Complex number.
A complex number is a number that can be expressed in the form a plus b, where a and b are real numbers and I is the imaginary unit, which satisfies the equation I2 equals 1. In this expression, a is the real part and b is the imaginary part of the complex number. Complex numbers extend the concept of the one-dimensional number line to the two-dimensional complex plane by using the horizontal axis for the real part and the vertical axis for the imaginary part. The complex number a plus b can be identified with a point in the complex plane. A complex number whose real part is 0 is said to be purely imaginary, whereas a complex number whose imaginary part is 0 is a real number. In this way the complex numbers contain the ordinary real numbers while extending them in order to solve problems that cannot be solved with real numbers alone. As well as their use within mathematics, complex numbers have practical applications in many fields, including physics, chemistry, biology, economics, electrical engineering, and statistics. The Italian mathematician Gerolamo Cardano is the first known to have introduced complex numbers. He called them fictitious during his attempts to find solutions to cubic equations in the 16th century.
Overview.
Complex numbers allow for solutions to certain equations that have no real solutions. The equation has no real solution, since the square of a real number is either 0 or positive. Complex numbers provide a solution to this problem. The idea is to extend the real numbers with the imaginary unit I where I2 equals 1, so that solutions to equations like the preceding one can be found. In this case the solutions are 1 plus 3i and 1, 3i, as can be verified using the fact that I2 equals 1. In fact not only quadratic equations, but all polynomial equations with real or complex coefficients in a single variable can be solved using complex numbers.
Definition.
A complex number is a number of the form a plus b, where a and b are real numbers and I is an imaginary unit, satisfying I2 equals 1. For example, 3.5 plus 2i is a complex number. The real number a is called the real part of the complex number a plus b. The real number b is called the imaginary part of a plus b. By this convention the imaginary part does not include the imaginary unit, hence b, not b, is the imaginary part. The real part of a complex number z is denoted by re, z, or z. The imaginary part of a complex number z is denoted by m, z, or z. For example, hence, in terms of its real and imaginary parts, a complex number z is equal to, this is sometimes known as the Cartesian form of z. A real number a can be regarded as a complex number a plus 0 or whose imaginary part is 0. A purely imaginary number b is a complex number 0 plus b whose real part is 0. It is common to write a for a plus 0i and b for 0 plus b. Moreover, when the imaginary part is negative, it is common to write a b with b greater than 0 instead of a plus b, I, for example 3. 4i instead of 3 plus 4i. The set of all complex numbers is denoted by, or.
Notation.
Some authors write a plus ib instead of a plus b. In some disciplines, in particular electromagnetism and electrical engineering, J is used instead of I, since I is frequently used for electric current. In these cases complex numbers are written as a plus bj or a plus jb.
Complex plane.
A complex number can be viewed as a point or position vector in a two-dimensional Cartesian coordinate system called the complex plane or Argand diagram, see Pedo 1988 and Solomons 2001, named after Jean-Robert Argand. The numbers are conventionally plotted using the real part as the horizontal component, and imaginary part as vertical, see Figure 1. These two values used to identify a given complex number are therefore called its Cartesian, rectangular, or algebraic form. A position vector may also be defined in terms of its magnitude and direction relative to the origin. These are emphasized in a complex number's polar form. Using the polar form of the complex number in calculations may lead to a more intuitive interpretation of mathematical results. Notably, the operations of addition and multiplication take on a very natural geometric character when complex numbers are viewed as position vectors. Addition corresponds to vector addition while multiplication corresponds to multiplying their magnitudes and adding their arguments, that is the angles they make with the x-axis. Viewed in this way, the multiplication of a complex number by I corresponds to rotating the position vector counterclockwise by a quarter turn, 90 deg, about the origin.
History in brief.
The solution in radicals, without trigonometric functions, of a general cubic equation contains the square roots of negative numbers when all three roots are real numbers, a situation that cannot be rectified by factoring aided by the rational root test if the cubic is irreducible, the so-called casus irreducibilis. This conundrum led Italian mathematician Gerolamo Cardano to conceive of complex numbers in around 1545, though his understanding was rudimentary. Work on the problem of general polynomials ultimately led to the fundamental theorem of algebra, which shows that with complex numbers, a solution exists to every polynomial equation of degree 1 or higher. Complex numbers thus form an algebraically closed field, where any polynomial equation has a root. Many mathematicians contributed to the full development of complex numbers. The rules for addition, subtraction, multiplication, and division of complex numbers were developed by the Italian mathematician Raphael Bombelli. A more abstract formalism for the complex numbers was further developed by the Irish mathematician William Rowan Hamilton, who extended this abstraction to the theory of quaternions.
Relations. Equality.
Two complex numbers are equal if and only if both their real and imaginary parts are equal. In symbols.
Ordering.
Because complex numbers are naturally thought of as existing on a two-dimensional plane, there is no natural linear ordering on the set of complex numbers. There is no linear ordering on the complex numbers that is compatible with addition and multiplication. Formally, we say that the complex numbers cannot have the structure of an ordered field. This is because any square in an ordered field is at least 0, but I2 equals -1.
Elementary operations. Conjugation.
The complex conjugate of the complex number z equals x plus y is defined to be x. Y. It is denoted or z. Formally, for any complex number z. Geometrically, is the reflection of z about the real axis. In particular, conjugating twice gives the original complex number. The real and imaginary parts of a complex number z can be extracted using the conjugate. Moreover, a complex number is real if and only if it equals its conjugate. Conjugation distributes over the standard arithmetic operations. The reciprocal of a non-zero complex number z equals x plus y is given by. This formula can be used to compute the multiplicative inverse of a complex number if it is given in rectangular coordinates. Inversive geometry, a branch of geometry studying reflections more general than ones about a line, can also be expressed in terms of complex numbers.
Addition and subtraction.
Complex numbers are added by adding the real and imaginary parts of the summands. That is to say. Similarly, subtraction is defined by using the visualization of complex numbers in the complex plane. The addition has the following geometric interpretation: the sum of two complex numbers a and b, interpreted as points of the complex plane, is the point x obtained by building a parallelogram 3 of whose vertices are O, A and B. Equivalently, x is the point such that the triangles with vertices O, A, B, and x, B, A, are congruent.
Multiplication and division.
The multiplication of two complex numbers is defined by the following formula. In particular, the square of the imaginary unit is 1. The preceding definition of multiplication of general complex numbers follows naturally from this fundamental property of the imaginary unit. Indeed, if I is treated as a number so that d means d times I, the above multiplication rule is identical to the usual rule for multiplying two sums of two terms. The division of two complex numbers is defined in terms of complex multiplication, which is described above, and real division, where at least one of C and D is non-zero. Division can be defined in this way because of the following observation. As shown earlier, C, D is the complex conjugate of the denominator C plus D. The real part C and the imaginary part D of the denominator must not both be zero for division to be defined.
Square root.
The square roots of a plus b, with b 0, are, where and where SGN is the signum function. This can be seen by squaring to obtain a plus b. Here is called the modulus of a plus b, and the square root with non-negative real part is called the principal square root.
Polar form. Absolute value and argument.
An alternative way of defining a point P in the complex plane, other than using the x and y coordinates, is to use the distance of the point from O, the point whose coordinates are 0, 0, the origin, together with the angle subtended between the positive real axis and the line segment OP in a counterclockwise direction. This idea leads to the polar form of complex numbers. The absolute value, or modulus or magnitude, of a complex number z equals x plus years. If z is a real number, that is, y equals 0, then r equals x. In general, by Pythagoras' theorem, r is the distance of the point P representing the complex number z to the origin. The argument or phase of z is the angle of the radius OP with the positive real axis, and is written as with the modulus, the argument can be found from the rectangular form. The value of pH must always be expressed in radians. It can increase by any integer multiple of 2p and still give the same angle. Hence, the arg function is sometimes considered as multi-valued. Normally, as given above, the principal value in the interval p is chosen. Values in the range 0 to p are obtained by adding 2p if the value is negative. The polar angle for the complex number 0 is indeterminate, but arbitrary choice of the angle 0 is common. The value of pH equals the result of at and 2. Together, r and pH give another way of representing complex numbers, the polar form, as the combination of modulus and argument fully specify the position of a point on the plane. Recovering the original rectangular coordinates from the polar form is done by the formula called trigonometric form. Using Euler's formula, this can be written as using the psi function, this is sometimes abbreviated to in angle notation, often used in electronics to represent a phasor with amplitude and phase pH, it is written as
multiplication and division in polar form.
Formulas for multiplication, division and exponentiation are simpler in polar form than the corresponding formulas in Cartesian coordinates. Given two complex numbers z1 equals a1, cos penthouse 1 plus I sin penthouse 1, and z2 equals a2, cos penthouse 2 plus I sin penthouse 2, because of the well-known trigonometric identities, we may derive. In other words, the absolute values are multiplied and the arguments are added to yield the polar form of the product. For example, multiplying by I corresponds to a quarter turn counterclockwise, which gives back I2 equals 1. The picture at the right illustrates the multiplication of. Since the real and imaginary part of 5 plus 5i are equal, the argument of that number is 45 degrees, or p/4, in radian. On the other hand, it is also the sum of the angles at the origin of the red and blue triangles are arctan, 1/3, and arctan, 1/2, respectively. Thus, the formula holds. As the arctan function can be approximated highly efficiently, formulas like this, known as Mac and like formulas, are used for high-precision approximations of P. Similarly, division is given by
exponentiation. Euler's formula.
Euler's formula states that, for any real number x, where e is the base of the natural logarithm, this can be proved by observing that, and so on, and by considering the Taylor series expansions of ex, cos, x, and sin, x. The rearrangement of terms is justified because each series is absolutely convergent.
Natural logarithm.
Euler's formula allows us to observe that, for any complex number, where r is a non-negative real number, one possible value for z's natural logarithm is. Because cos and sin are periodic functions, the natural logarithm may be considered a multi-valued function, with
integer and fractional exponents.
We may use the identity to define complex exponentiation, which is likewise multi-valued. Where n is an integer, this simplifies to de Moivre's formula. The nth roots of z are given by, for any integer k satisfying 0, k, n, 1. Here n, r is the usual, positive, nth root of the positive real number r. While the nth root of a positive real number r is chosen to be the positive real number c satisfying Cn equals x, there is no natural way of distinguishing one particular complex nth root of a complex number. Therefore, the nth root of z is considered as a multi-valued function, in z, as opposed to a usual function f, for which f, z, is a uniquely defined number. Formulas such as which holds for positive real numbers, do in general not hold for complex numbers.
Properties. Field structure.
The set C of complex numbers is a field. Briefly, this means that the following facts hold. First, any two complex numbers can be added and multiplied to yield another complex number. Second, for any complex number z, its additive inverse, z is also a complex number. And third, every non-zero complex number has a reciprocal complex number. Moreover, these operations satisfy a number of laws, for example the law of commutativity of addition and multiplication for any two complex numbers z1 and z2. These two laws and the other requirements on a field can be proven by the formulas given above, using the fact that the real numbers themselves form a field. Unlike the reals, C is not an ordered field, that is to say, it is not possible to define a relation z1 less than z2 that is compatible with the addition and multiplication. In fact, in any ordered field, the square of any element is necessarily positive, so I2 equals 1 precludes the existence of an ordering on C. When the underlying field for a mathematical topic or construct is the field of complex numbers, the thing's name is usually modified to reflect that fact. For example, complex analysis, complex matrix, complex polynomial, and complex Lie algebra.
Solutions of polynomial equations.
Given any complex numbers, called coefficients, AO, and the equation has at least one complex solution Z, provided that at least one of the higher coefficients A1, n is non-zero. This is the statement of the fundamental theorem of algebra. Because of this fact, C is called an algebraically closed field. This property does not hold for the field of rational numbers Q, the polynomial x2. 2 does not have a rational root, since 2 is not a rational number, nor the real numbers are. The polynomial x2 plus a does not have a real root for a greater than 0, since the square of x is positive for any real number x. There are various proofs of this theorem either by analytic methods such as Liouville's theorem, or topological ones such as the winding number, or a proof combining Galois theory and the fact that any real polynomial of odd degree has at least one real root. Because of this fact, theorems that hold for any algebraically closed field, apply to C. For example, any non-empty complex square matrix has at least one complex eigenvalue.
Algebraic characterization.
A field C has the following three properties. First, it has characteristic 0. This means that 1 plus 1 plus 1, 0 for any number of summands, all of which equal 1. Second, its transcendence degree over Q, the prime field of C, is the cardinality of the continuum. Third, it is algebraically closed, see above. It can be shown that any field having these properties is isomorphic, as a field, to C. For example, the algebraic closure of QP also satisfies these three properties, so these two fields are isomorphic. Also, C is isomorphic to the field of complex Poisson. However, specifying an isomorphism requires the axiom of choice. Another consequence of this algebraic characterization is that C contains many proper subfields that are isomorphic to C.
Characterization as a topological field.
The preceding characterization of C describes the algebraic aspects of C, only. That is to say, the properties of nearness and continuity, which matter in areas such as analysis and topology, are not dealt with. The following description of C as a topological field, that is, a field that is equipped with a topology, which allows the notion of convergence, does take into account the topological properties. C contains a subset P, namely the set of positive real numbers, of non-zero elements satisfying the following three conditions. P is closed under addition, multiplication and taking inverses. If x and y are distinct elements of P, then either x, y or y. X is in P. If S is any non-empty subset of P, then S plus P equals X plus P for some x in C. Moreover, C has a non-trivial involutive automorphism X, namely the complex conjugation, such that X is in P for any non-zero x in C. Any field F with these properties can be endowed with a topology by taking the sets B, X, P, equals Y P. Y. X, Y. X. P is a base, where X ranges over the field and P ranges over P. With this topology F is isomorphic as a topological field to C. The only connected locally compact topological fields are R and C. This gives another characterization of C as a topological field, since C can be distinguished from R because the non-zero complex numbers are connected, while the non-zero real numbers are not.
Formal construction. Formal development.
Above, complex numbers have been defined by introducing I, the imaginary unit, as a symbol. More rigorously, the set C of complex numbers can be defined as the set A2 of ordered pairs, A, B, of real numbers. In this notation, the above formulas for addition and multiplication read. It is then just a matter of notation to express A, B, as A plus B. Though this low-level construction does accurately describe the structure of the complex numbers, the following equivalent definition reveals the algebraic nature of C more immediately. This characterization relies on the notion of fields and polynomials. A field is a set endowed with an addition, subtraction, multiplication and division operations that behave as is familiar from, say, rational numbers. For example, the distributive law must hold for any three elements x, y and z of a field. The set R of real numbers does form a field. A polynomial p, x, with real coefficients is an expression of the form where the a,o and are real numbers. The usual addition and multiplication of polynomials endows the set R of all such polynomials with a ring structure. This ring is called polynomial ring. The quotient ring x2 plus 1, can be shown to be a field. This extension field contains two square roots of 1, namely, the cosets of x and x, respectively. The cosets of 1 and x form a basis of a x2 plus 1, as a real vector space, which means that each element of the extension field can be uniquely written as a linear combination in these two elements. Equivalently, elements of the extension field can be written as ordered pairs, A, B, of real numbers. Moreover, the above formulas for addition etc. correspond to the ones yielded by this abstract algebraic approach. The two definitions of the field C are said to be isomorphic, as fields. Together with the above-mentioned fact that C is algebraically closed, this also shows that C is an algebraic closure of R.
Matrix representation of complex numbers.
Complex numbers A plus IP can also be represented by 2x2 matrices that have the following form. Here the entries A and B are real numbers. The sum and product of two such matrices is again of this form, and the sum and product of complex numbers corresponds to the sum and product of such matrices. The geometric description of the multiplication of complex numbers can also be phrased in terms of rotation matrices by using this correspondence between complex numbers and such matrices. Moreover, the square of the absolute value of a complex number expressed as a matrix is equal to the determinant of that matrix. The conjugate corresponds to the transpose of the matrix. Though this representation of complex numbers with matrices is the most common, many other representations arise from matrices other than that square to the negative of the identity matrix. See the article on 2x2 real matrices for other representations of complex numbers.
Complex analysis.
The study of functions of a complex variable is known as complex analysis and has enormous practical use in applied mathematics as well as in other branches of mathematics. Often, the most natural proofs for statements in real analysis or even number theory employ techniques from complex analysis. See prime number theorem for an example. Unlike real functions, which are commonly represented as two-dimensional graphs, complex functions have four-dimensional graphs and may usefully be illustrated by color-coding a three-dimensional graph to suggest four dimensions, or by animating the complex function's dynamic transformation of the complex plane.
Complex exponential and related functions.
The notions of convergent series and continuous functions in real analysis have natural analogues in complex analysis. A sequence of complex numbers is said to converge if and only if its real and imaginary parts do. This is equivalent to the E.D. definition of limits, where the absolute value of real numbers is replaced by the one of complex numbers. From a more abstract point of view, C, endowed with a metric, is a complete metric space, which notably includes the triangle inequality. For any two complex numbers Z1 and Z2. Like in real analysis, this notion of convergence is used to construct a number of elementary functions. The exponential function exp, z, also written as, is defined as the infinite series. And the series defining the real trigonometric functions sine and cosine, as well as hyperbolic functions such as sin also carry over to complex arguments without change. Euler's identity states, for any real number pH, in particular. Unlike in the situation of real numbers, there is an infinitude of complex solutions Z of the equation. For any complex number W, 0, it can be shown that any such solution Z, called complex logarithm of A, satisfies. Where arg is the argument defined above, and ln the real, natural logarithm. As arg is a multi-valued function, unique only up to a multiple of 2p, log is also multi-valued. The principal value of log is often taken by restricting the imaginary part to the interval p. Complex exponentiation ZO is defined as. Consequently, they are in general multi-valued. For O equals 1/n, for some natural number n, this recovers the non-uniqueness of nth roots mentioned above. Complex numbers, unlike real numbers, do not in general satisfy the unmodified power and logarithm identities, particularly when naively treated as single-valued functions. See failure of power and logarithm identities. For example, they do not satisfy. Both sides of the equation are multi-valued by the definition of complex exponentiation given here, and the values on the left are a subset of those on the right.
Holomorphic functions.
A function f, c is called holomorphic if it satisfies the Cauchy-Riemann equations. For example, any linear map C can be written in the form with complex coefficients a and b. This map is holomorphic if and only if b equals 0. The second summand is real differentiable, but does not satisfy the Cauchy-Riemann equations. Complex analysis shows some features not apparent in real analysis. For example, any two holomorphic functions f and g that agree on an arbitrarily small open subset of C necessarily agree everywhere. Meromorphic functions that can locally be written as f, z, z, zo, n with a holomorphic function f, still share some of the features of holomorphic functions. Other functions have essential singularities, such as sin, 1/z, at z equals 0.
Applications.
Complex numbers have essential concrete applications in a variety of scientific and related areas such as signal processing, control theory, electromagnetism, fluid dynamics, quantum mechanics, cartography, and vibration analysis. Some applications of complex numbers are:
Control theory.
in control theory, systems are often transformed from the time domain to the frequency domain using the Laplace transform. The system's poles and zeros are then analyzed in the complex plane. The root locus, Nyquist plot, and Nichols plot techniques all make use of the complex plane. In the root locus method, it is especially important whether the poles and zeros are in the left or right half planes, that is have real part greater than or less than 0. If a linear, time-invariant, LTI, system has poles that are in the right half plane, it will be unstable, or in the left half plane, it will be stable. On the imaginary axis, it will have marginal stability. If a system has zeros in the right half plane, it is a non-minimum phase system.
Improper integrals.
In applied fields, complex numbers are often used to compute certain real-valued improper integrals, by means of complex-valued functions. Several methods exist to do this. See methods of contour integration.
Fluid dynamics.
In fluid dynamics, complex functions are used to describe potential flow in 2 dimensions.
Dynamic equations.
In differential equations, it is common to first find all complex roots are of the characteristic equation of a linear differential equation or equation system and then attempt to solve the system in terms of base functions of the form f, t, equals et. Likewise, in difference equations, the complex roots are of the characteristic equation of the difference equation system are used, to attempt to solve the system in terms of base functions of the form f, t, equals a t.
Electromagnetism and electrical engineering.
In electrical engineering, the Fourier transform is used to analyze varying voltages and currents. The treatment of resistors, capacitors, and inductors can then be unified by introducing imaginary, frequency-dependent resistances for the latter two and combining all three in a single complex number called the impedance. This approach is called phasor calculus. In electrical engineering, the imaginary unit is denoted by J, to avoid confusion with I, which is generally in use to denote electric current. Since the voltage in an AC circuit is oscillating, it can be represented as. To obtain the measurable quantity, the real part is taken. See for example.
Signal analysis.
Complex numbers are used in signal analysis and other fields for a convenient description for periodically varying signals. For given real functions representing actual physical quantities, often in terms of sines and cosines, corresponding complex functions are considered of which the real parts are the original quantities. For a sine wave of a given frequency, the absolute value z of the corresponding z is the amplitude and the argument arg, z, the phase. If Fourier analysis is employed to write a given real-valued signal as a sum of periodic functions, These periodic functions are often written as complex-valued functions of the form where O represents the angular frequency and the complex number Z encodes the phase and amplitude as explained above. This use is also extended into digital signal processing and digital image processing, which utilize digital versions of Fourier analysis and wavelet analysis to transmit, compress, restore, and otherwise process digital audio signals, still images, and video signals. Another example, relevant to the two side bands of amplitude modulation of AM radio, is
quantum mechanics.
The complex number field is intrinsic to the mathematical formulations of quantum mechanics, where complex Hilbert spaces provide the context for one such formulation that is convenient and perhaps most standard. The original foundation formulas of quantum mechanics, the Schrödinger equation and Heisenberg's matrix mechanics, make use of complex numbers.
Relativity.
In special and general relativity, some formulas for the metric on spacetime become simpler if one takes the time variable to be imaginary. This is no longer standard in classical relativity, but is used in an essential way in quantum field theory. Complex numbers are essential to spinors, which are a generalization of the tensors used in relativity.
Geometry. Fractals.
Certain fractals are plotted in the complex plane, for example the Mandelbrot set and Julia sets.
Triangles.
Every triangle has a unique Steinerian ellipse, an ellipse inside the triangle and tangent to the midpoints of the three sides of the triangle. The foci of a triangle's Steinerian ellipse can be found as follows, according to Marden's theorem. Denote the triangle's vertices in the complex plane as A equals xa plus yi, B equals xb plus yb, and C equals xc plus yci. Write the cubic equation, take its derivative, and equate the quadratic derivative to 0. Marden's theorem says that the solutions of this equation are the complex numbers denoting the locations of the two foci of the Steinerian ellipse.
Algebraic number theory.
As mentioned above, any non-constant polynomial equation, in complex coefficients, has a solution in Ca fortiori. The same is true if the equation has rational coefficients. The roots of such equations are called algebraic numbers. They are a principal object of study in algebraic number theory. Compared to Q, the algebraic closure of Q, which also contains all algebraic numbers, C has the advantage of being easily understandable in geometric terms. In this way, algebraic methods can be used to study geometric questions and vice versa. With algebraic methods, more specifically applying the machinery of field theory to the number field containing roots of unity, it can be shown that it is not possible to construct a regular nonagon using only compass and straightedge, a purely geometric problem. Another example are Gaussian integers, that is, numbers of the form x plus I, where x and y are integers, which can be used to classify sums of squares.
Analytic number theory.
Analytic number theory studies numbers, often integers or rationals, by taking advantage of the fact that they can be regarded as complex numbers, in which analytic methods can be used. This is done by encoding number theoretic information in complex valued functions. For example, the Riemann zeta function z, s, is related to the distribution of prime numbers.
History.
The earliest fleeting reference to square roots of negative numbers can perhaps be said to occur in the work of the Greek mathematician Hero of Alexandria in the 1st century AD, where in his Stereometrica he considers, apparently in error, the volume of an impossible frustum of a pyramid to arrive at the term 81. 144 in his calculations, although negative quantities were not conceived of in Hellenistic mathematics and Heron merely replaced it by its positive. The impetus to study complex numbers proper first arose in the 16th century when algebraic solutions for the roots of cubic and quartic polynomials were discovered by Italian mathematicians, see Niccolò Fontana Tartaglia, Gerolamo Cardano. It was soon realized that these formulas, even if one was only interested in real solutions, sometimes required the manipulation of square roots of negative numbers. As an example, Tartaglia's formula for a cubic equation of the form gives the solution to the equation x3 equals x as. At first glance this looks like nonsense. However, formal calculations with complex numbers show that the equation z3 equals I has solutions I, and. Substituting these in turn for in Tartaglia's cubic formula and simplifying, one gets 0, 1 and 1 as the solutions of x3. X equals 0. Of course this particular equation can be solved at sight, but it does illustrate that when general formulas are used to solve cubic equations with real roots, then, as later mathematicians showed rigorously, the use of complex numbers is unavoidable. Raphael Bombelli was the first to explicitly address these seemingly paradoxical solutions of cubic equations and developed the rules for complex arithmetic trying to resolve these issues. The term imaginary for these quantities was coined by René Descartes in 1637, although he was at pains to stress their imaginary nature. A further source of confusion was that the equations seemed to be capriciously inconsistent with the algebraic identity, which is valid for non-negative real numbers a and b, and which was also used in complex number calculations with one of a, b positive and the other negative. The incorrect use of this identity, and the related identity, in the case when both a and b are negative, even bedeviled Euler. This difficulty eventually led to the convention of using the special symbol I in place of 1 to guard against this mistake. Even so, Euler considered it natural to introduce students to complex numbers much earlier than we do today. In his elementary algebra textbook, Elements of Algebra, he introduces these numbers almost at once and then uses them in a natural way throughout. In the 18th century, complex numbers gained wider use, as it was noticed that formal manipulation of complex expressions could be used to simplify calculations involving trigonometric functions. For instance, in 1730 Abraham de Moivre noted that the complicated identities relating trigonometric functions of an integer multiple of an angle to powers of trigonometric functions of that angle could be simply re-expressed by the following well-known formula which bears his name, de Moivre's formula. In 1748 Leonhard Euler went further and obtained Euler's formula of complex analysis. By formally manipulating complex power series and observed that this formula could be used to reduce any trigonometric identity to much simpler exponential identities. The idea of a complex number as a point in the complex plane, above, was first described by Caspar Wessel in 1799, although it had been anticipated as early as 1685 in Wallace's De Algebra Tractatus. Wessel's memoir appeared in the Proceedings of the Copenhagen Academy but went largely unnoticed. In 1806 John Robert Argand independently issued a pamphlet on complex numbers and provided a rigorous proof of the fundamental theorem of algebra. Gauss had earlier published an essentially topological proof of the theorem in 1797 but expressed his doubts at the time about the true metaphysics of the square root of 1 inch. It was not until 1831 that he overcame these doubts and published his treatise on complex numbers as points in the plane, largely establishing modern notation and terminology. The English mathematician G. H. Hardy remarked that Gauss was the first mathematician to use complex numbers in a really confident and scientific way, although mathematicians such as Niels Henrik Abel and Carl Gustav Jacob Jacobi were necessarily using them routinely before Gauss published his 1831 treatise. Augustin Louis Cauchy and Bernhard Riemann together brought the fundamental ideas of complex analysis to a high state of completion, commencing around 1825 in Cauchy's case. The common terms used in the theory are chiefly due to the founders. Argand called the direction factor, and the modulus. Cauchy, 1828, called the reduced form, l'expression réduite, and apparently introduced the term argument. Gauss used I4, introduced the term complex number for a plus b, and called a2 plus b2 the norm. The expression direction coefficient, often used for, is due to Hankel, 1867, and absolute value, for modulus, is due to Weierstrass. Later classical writers on the general theory include Richard Dedekind, Otto Holder, Felix Klein, Henri Poincaré, Hermann Schwarz, Carl Weierstrass and many others.
Generalizations and related notions.
The process of extending the field R of reals to C is known as Cayley-Dickson construction. It can be carried further to higher dimensions, yielding the quaternions H and octonions O which, as a real vector space, are of dimension 4 and 8, respectively. However, just as applying the construction to reals loses the property of ordering, more algebraic properties familiar from real and complex numbers vanish with increasing dimension. The quaternions are only a skew field, that is for some x, y, xy. Yx for two quaternions, the multiplication of octonions fails, in addition to not being commutative, to be associative, for some x, y, z, xy, z. X, y, z. Reals, complex numbers, quaternions and octonions are all normed division algebras over R. However, by Hurwitz's theorem they are the only ones. The next step in the Cayley-Dickson construction, the settonions, in fact fails to have this structure. The Cayley-Dickson construction is closely related to the regular representation of C, thought of as an R algebra, and a vector space with a multiplication, with respect to the basis, 1, I. This means the following: the R linear map for some fixed complex number W can be represented by a 2x2 matrix, once a basis has been chosen. With respect to the basis, 1, I, this matrix is, that is, the one mentioned in the section on matrix representation of complex numbers above. While this is a linear representation of C in the 2x2 real matrices, it is not the only one. Any matrix has the property that its square is the negative of the identity matrix, J2 equals I. Then is also isomorphic to the field C, and gives an alternative complex structure on A2. This is generalized by the notion of a linear complex structure. Hypercomplex numbers also generalize R, C, H, and O. For example, this notion contains the split complex numbers, which are elements of the ring A/x2. 1, as opposed to A/x2 plus 1. In this ring, the equation A2 equals 1 has 4 solutions. A field R is the completion of Q, the field of rational numbers, with respect to the usual absolute value metric. Other choices of metrics on Q led to the fields QP of p-adic numbers, for any prime number p, which are thereby analogous to R. There are no other non-trivial ways of completing Q than and QP, by Ostrowski's theorem. The algebraic closure of QP still carry a norm, but, unlike C, are not complete with respect to it. The completion of turns out to be algebraically closed. This field is called p-adic complex numbers by analogy. The fields R and QP in their finite field extensions, including C, are local fields.